And the clicker. Okay, perfect. All right, morning everybody. First, I mean, after seeing the enthusiastic collection of students in class, I get the feeling that maybe Wednesday's class isn't worth it. Also, kind of my brain's checked out, right? I went to pick up my brains today morning and I found a note like, gone on vacations, enjoy the semester. So I'm just going to be wrapping up reinforcement learning today. What I was planning on doing in the next class was tying it up with everything we've done earlier in the semester. You'll notice that a specific topic was conspicuously absent from the past 4 lectures and also from today's lectures, namely deep neural networks or neural networks of any kind. So they'll continue to remain absent because I'm taking Wednesday off. I'll leave the reading up to you, but you should be able to put 2 and 2 together, all things considered, right? So quick recap. What is the time? 9:05 a.m., right? We were talking about reinforcement learning, but well, this is wrong. We're not defining MDPs anymore. We're done with that and planning. What we really spoke of in the past 4 classes was about, well, we got to that point where you basically didn't understand anything. And today's class, for the first time, I'm going to be writing focusing and squiggles. Figures, but I realized that once I begin trying to explain things with figures, it's going to take a lot more time. So it's going to be pretty steep. What we have covered is a basic definition of Markov processes, the notion of an information state in Markov processes, meaning that we are modeling everything in terms of the information state, not the physical state of the system. We spoke of Markov reward processes, which is basically a Markov process where every state stochastic gives you a reward. And then we had a Markov, so this was the fly Markov reward process model, as you saw, and we noticed the difference between the physical state and the information state. Here the information state, although the system is very simple, the way we define the information state here was in terms of the distance from the spider, not the actual position on the cube, right? And then we spoke of a discounted return, and this was the key to everything. When you have a reward process of any kind, at every state, every time you visit a state or every time you take a specific, okay, we haven't yet gotten to actions. Every time you visit a state, you actually get a reward. And so you can spend, which is a discounted sum of rewards all the way into the horizon when you're at any state, which gives you an idea of how valuable it is to be at that state, because that value gives you an idea of how much you can expect to earn if you are at that state at any time. Then we spoke of Markov decision processes, which are Markov reward processes with a small difference. The agent had real agency. They could choose their actions, and the agent's actions would modify the environment behavior. We saw a specific example of this with the fly and spider problem, where if the agent, the spider, went closer to the fly moved. And we ended up, and we saw that when you have behavior of this kind, the transition probabilities of the system, of the environment, are really dependent on the action that the agent takes. Here, for example, if the spider was moving away from the fly, you were deterministically increasing the distance to the fly. But if the spider was moving closer to the fly, then the process became stochastic, right? We noted the notion of a policy, which is some kind of a policy on action to take at any state. This could be stochastic, this could be deterministic, and in general, when you are in a system of this kind, you want to choose a policy that maximizes the total return that you're going to get, which means in turn that you must maximize the total return at every state. We spoke of the value of a system, of a state in this whole process, which was how valuable it was to be at any state, which basically was the expected return into the horizon if you happen to be at that state at any time. And so this was simply if assuming that rewards and transition probabilities were action specific, then based on the action that you took on the state, each action begat a specific return, and the expectations over the returns for all possible actions gave you the value for the state. And of course, the return for a specific action from a state gave you the action value function for the state action combination, right? We've seen all of this. This was all familiar. We spoke of optimal policies, where the optimal policy is the policy that will maximize the expected total discounted reward at every state. So you want to, the expected total discounted reward is simply the expectation of the reward, of the return, expectation of the return if you happen to be at that state. We saw that the return itself was stochastic. Each run through the system is going to give you a total return, but there's an expected value because it's a distribution, meaning if you did the whole thing again and again and again, the average would converge to some value. The average would converge to some value, and that's the expected value of the return for the state. That's what you wanted to maximize for every state, and we found that there's something called an optimal policy theorem, which states that there are one or more policies which are optimal, in the sense that if you follow that policy, this return is the maximum you can ever get for that state, right? And so for the optimal policy, the value of each state was greater than or equal to the value of the state under any other policy. The value of each state action combination was also greater than or equal to the value of the state action combination under any other policy, right? So and of course, once we specified all of this, it was very easy for us to decide what an optimal policy was at any state. You wanted to take the action that had the maximum return, right? Why would you take any other action? Why would you choose an action where the expected return was lesser than it could possibly be? So the optimal policy at any state was to choose the action, the result that resulted in the largest expected return, the largest state action value, right? So which of course gave us that the corresponding optimal value for any state was simply the largest amongst all actions of the state action values under the same policy, which gave us the Bellman optimality equation, right? And then we spoke of planning with a Markov decision process, which is to say somebody has given us the Markov decision process. What are the states? What are the transition probabilities? What are the probability distributions over rewards? And what is the discounting factor? All of these things, right? So given all of these, the idea was to come up with an optimal policy for every state. This was called planning. When the decision process is defined for you, you have to come up with an optimal policy for every state, right? And we saw two possible ways of doing this. There was a value-based solution and a policy-based solution. The way we broke it down, the value-based solution, was that given any policy, we found out the optimal, we found out the values for all the states under the policy. But then once you found the values for all of the states, you could revise your policy to choose the, greedily choose the most valuable action at each state, and that would modify the policy. So you had the prediction, which determined the values for the states, and then you had the control, which chose the optimal policy or the greedily best policy under the values that you computed. But using the new policy, you could go back and relearn the values. And then once you relearn the values, you could go back and estimate the policy. This was our overall solution. This gave us two solutions. The first one was, so this was the dynamic programming solution for how you found the values for the states given a policy. And then we came up with a policy iteration, which basically said you start off with some random policy, then use the prediction dynamic programming to compute the values for all the states, then greedily update your policy by greedily choosing the best action at each state and iterate the whole process. We also saw the value iteration, which iteratively computed the optimal value for each state, or the value of each state under the optimal policy. It was an iterative algorithm. you went through it, and eventually it gave you the optimal value for each state. All of this was a quick recap, right? So everybody's familiar with it. Even if you don't remember all of it, it must have sort of rung a bell somewhere in the back of your head, right? Considering that it's been a few days. So the problem so far, given all the details of the Markov decision process, we were computing the optimal value function, we were computing optimal action value functions, and we were computing optimal policies. This was planning, right? In real life, nobody is going to give us the Markov decision process. So, if I say I'm out in the, this is not not supposed to be an entirely theoretical concept, right? Construct. And even in situations where you can actually, somebody does give you the MDP, this is going to be non-trivial. Think about a chess game. There are 10 raised to 120 states. Think about Go. There are 10 raised to 160 states. There's no way you're going to be able to perform all of these computations, right? So we want to see how we can actually learn the optimal policy when we are not given the MDP. And so here we're going to look at model-free methods. Again, there's a bit of there's a little bit of a confusion in the terminology, in the sense that when I'm speaking of model-free methods over here, I'm just speaking of solutions where nobody gave you the MDP, right? And yet you're supposed to learn how to behave within the system. Now, in this is what we will call reinforcement learning. When you are not given the Markov decision process, nevertheless, you will assume that there's an underlying MDP, and you must learn the optimal policy for each state. So this is reinforcement learning. So far, we haven't spoken of reinforcement learning. We've set up a base. But as it turns out, the rest of today's to do the next class, I'm going to give you only every class, in each of the classes so far, I gave you a few surprising facts. Today there are only 3 surprises. So it's really very small. Everything, the rest of it is something you would have come up with on your own if you just sat down with a pen and paper, or even without a pen and paper, spend a little more time working it out in your head. And you'll see why it's so easy, right? How do you find this? What we are doing, reinforcement learning. Specifically, we are not going to construct the MDP over here. We're just going to try to learn the policy. There's a variant of this called model-based reinforcement learning, where you'll try to construct a model and then learn a policy, but I'm not going to get to that today, okay? So how do you find the value of a policy without knowing the underlying MDP? So we're going to perform, you want to find the values. I have some policy. I haven't given you the state transitions or the reward distributions. I must find the values. Remember, when I was given the MDP, that was called prediction, right? So this is model-free prediction. And how do I find the optimal policy? This was control. So now this is model-free control. And the assumption we're going to make is that although we are assuming we don't know the MDP, we can identify the states. I know what the states of the system are, or at least I'm modeling the states in a specific manner. So I have a model for the states. I just don't know the transition probabilities, right? I also know what actions I can perform. If I don't know what actions I can perform, there's really nothing I can do, right? I'm just stuck. I'm ignorant. So I'm going to assume I know what the actions I can perform are. These are the only 2 assumptions we're going to make. We know this. We have a model, or we know the states of the system. We know what we can do. And now, given we don't know anything about the system dynamics, we know how to measure rewards, because rewards are something that we get, right? This is the situation that we're going to be working with. I'm going to continue to assume discrete state, but it's fairly straightforward to update this to continuous state. So the model-free assumption is something like this. You can see the fly. You know the distance to the fly, so you know the state, right? You know the possible actions. You can get closer or farther, but you don't know the environment. You have no idea if how the fly is going to behave. Is it going to stay? Is it going to jump? If it jumps, what kind of behavior does the fly have, right? So considering this, first, let's say I have a system over here. I have some idea of how I behave whenever I'm in any state, right? So now, how do you find the value of a policy without knowing the underlying Markov decision process? Remember, we don't have transition probabilities anymore. All you know is I'm in the state. So remember, you'll remember that we sort of separated the probability distributions over actions from the transition probability or probabilities of the Markov process in the earlier definition of the entire model. There was a reason to do this, and the reason was building up to this, that it should be possible to define a choice of action without knowing the transition probabilities of the system itself. So this is why I say I know what actions I can take when I'm in any, even though I don't know anything about the underlying system. Given this means I can define a policy. How do I define the value of the policy? Right? How do I compute the value of the policy? So I can see the fly, I can see the distance to the fly. I have no idea of how the fly will respond to actions, but I have a policy. I'm always going to try to reduce the distance to the fly. What is the value of being at a distance d from the fly under this policy? This is the question I'd be asking in this setting, right? And there are several methods. All of them are fairly obvious. Like I said, I'm going to be introducing only 3 surprising facts if I manage to stuff all of them in the remaining time. So we're going to perform Monte Carlo learning, which is something that would be obvious to you. There would be no surprises. The first surprise is when I get to TD1. The second surprise is going to be when I get to TD lambda. And the third one is going to be when I get to Q learning. Okay? So, but let's look at the first and simplest method. If I don't know anything about the system, what is the most obvious thing to do? Just wander through the system and figure out things for myself, right? Monte Carlo, I have the system. Okay, what is the value of this policy at this state? Let me just perform the action. I'm going to get somewhere. I'm going to keep repeating this process at each state. I choose an action according to my policy. Eventually, I get to, maybe at some point this sequence terminates. Then I start and do the whole thing again. Eventually, I'm going to aggregate lots of observations. I can begin counting. I get my values, right? So here's what we take. You'd record what I'm going to call an episode is one run through the system, which may not have a natural termination. If it doesn't have a natural, I could just decide this is where I stop and start again. So you record several episodes where you take actions according to your policy and note states visited and rewards obtained as a result. So I'm just walking through the system. I'm going to say, okay, at time 1, I'm at state S1. I took action A1 according to my policy. I got a reward. And remember this strange notation where we had where the reward was associated with the next time. So it's R2. This causes some grief in our notation downstream. I just took it from Sutton and Bartow, right? So to perform this action A1, my state is going to have changed. I'm going to end up in S2, right? The world changed. Something happened. The traffic moved. The fly jumped. Something happened. My state changed. So at that state, now I'm going to choose, for that state, I have a plan, right? I have a policy. And according to that policy, I'm going to perform an action A2. And I promptly get the reward R3, and then the system changes. I keep doing this. And so eventually, I'm going to get an entire episode of this kind, right? Now recall that the value function is for any state is the expected return for the state, which is the expected value of this guy, right? I'm in state S. What is the discounted sum of rewards going all the way to the end from that point, which is going to be RT plus 1 plus gamma times RT plus 2 all the way to the end. The capital R is the random variable, right? The small r is the actual observation, given that the state is S. So what we are going to do is we are going to replace this expectation over here by the empirical average. It's a common enough thing, right? This is what we always do, correct? So here's what we can do. So here are all the episodes that I've recorded. I've played the game like I'm playing a game of chess against the computer. I took actions at each, at each state. The game ended, then I played another game, I played another game, I played another game, I played another game again. This is not chess, it has a fewer number of states, but you get the idea, right? And now, look at this. Within each episode, at each time, I can compute the return. right? At time 1, what is the return going to be? The return is going to be the first reward that I saw, plus gamma times the next reward I saw 2 steps up front, plus gamma squared times the reward I saw, 3 steps up front. So I'm over here, I've run through the entire episode, then I went back to the beginning and I'm looking down what I have experienced already. So this is not like I'm doing this as I proceed, right? I played the game, then I went back and I'm introspecting. And when I'm introspecting, I'm standing at the beginning of the game and say, okay, over here, what was the return I got? I can compute it. Then I can take 1 step forward and say, what over here, what was the return I got? Then I can take another step forward, and over here, what is the return I got, right? And I can compute this return for every time step. The formulae are irrelevant. You get the idea of exactly what I'm doing. If you wrote code for it, it would be trivial for you to compute this, correct? Done. So how would you do it? Now, when you through this episode, you visited the state SA a certain number of times, correct? Like if you were the spider, you're distance of 3 a certain times in each episode before you caught the fly. And then you went back, another fly descended on the cube, and you'd be doing the same thing. You'd find yourself, as you went through another episode, you're going to find yourself at a distance of 3 a certain number of times, right? And so this might be distance 3. This is again distance 3. Somewhere here is distance 3, and so on, right? So those are all the instances of visiting a specific state. Remember, this whole thing is still being assumed to be Markov. So to compute the expected value of the state over here, right, I just have to pick up the returns that I got over all the instances where I visited the state, and I just average them up, right? And this is going to give me an estimate for the value for that state. Very easy. No? Correct, but conceptually very easy. I'm speaking of conceptually, right? I'm not going to even begin dealing with this business of too many in this class, but the generalization is fairly straightforward. Okay. Keep thinking of tic-tac-toe or backgammons, games with a small number of state spaces, or many actions in the real world which really do have a small number of states. Okay. Now, so here's how you could actually process implement the whole thing. The number of times I visited any state is 0 in the beginning, and then for each episode, as I run through the episode, then I get back to the beginning, and for each time t, and then I sort of revisit the episode. I go back through it in my introspective process, and at each time t, I can compute the return, right, the actual return at that time, and then I can increment. I just say, okay, what is the state I was in? I increment the count for the state. I increment I increment the total return for the state. And when I'm done with all the episodes, I just divide the one by the other. I get back the values for the states. And now this is really a horrible way of doing it. There's a better way of doing it, which is to not store so many buffers. I won't actually get through this. This is just a slightly more efficient way of implementing exactly the same logic. But then, here's what it is. Here's what we get. You're learning from experience explicitly. After a sufficiently large number of episodes in which all states have been visited a sufficiently large number of times, we will obtain good estimates of the value functions of all the states. So what I've given you so far is not one of the surprises I was going to introduce. Was there anything surprising about this? This was the obvious thing to be doing, right? If you're going to be learning, this is the obvious thing to be doing. This is exactly what the counting-based estimation is all about. This was for value functions. I can easily enough extend it to action value pairs. I go through an episode, right? And at each point, I can compute the return. Now, for each action value pair, I can find all instances of that action value pair. State action pair for each state and action, and compute my state action value using that particular you just by averaging over all of my observations, right? So anything confusing so far? No, right? This is where we're going to build up on this. So this is just a little algorithm explaining exactly the same thing. Now this is the Monte Carlo approach. Why Monte Carlo? You just run through the system. This is exactly what Monte Carlo simulations are about, right? You run through the system and you compute your aggregate your statistics. Easy. The good thing is you're eventually guaranteed to get to the right answer. It's an unbiased estimate, meaning whatever estimate that you get, the expected value of the estimate is the true value for the variable you're trying to estimate. So if I compute state values, values for states, whatever estimate I get, the expected value of that estimate is going to be the true value for the state. So it's a good substitute. There is a problem over here. It's based heavily on introspection, meaning I have to play the episode to the end, then I have to come back to the beginning, and then I have to compute I have to go back through it a second time. And the reason I had to do this was that I was computing returns. And the only way I could compute a return was to say, what is the reward now, plus what is gamma times the reward of the next instant, plus what is gamma squared times the reward 2 instances out, and so on. So we are going to, and because we need to compute this sum of discounted rewards all the way to the end, you had to play the entire episode and then come back and repeat this. Now what if you're stuck in a game? Think of the spider and the fly, right? You happen to choose a really crappy policy which has a very, very small probability that you're going to catch the fly. You are never going to know the value of what you're doing because you keep running and running and running, you never catch the fly, right? So this is really going to be dependent on, whereas what you would like to do is to say, I've spent an hour and I still haven't caught the fly, maybe I should change my policy. So this is, you need to be able to learn on the fly, and something like this doesn't really help you. If you have to run through the episode before you can learn anything, it's not a great idea. And think of here's another problem. The returns that we compute are high variance. Why is that? When I'm computing a return as the sum of the reward over here, plus the reward at the next instant, plus the reward 2 instances out, each one of these, in a single run through the process, each one of these is a random variable, right? So the return that I'm actually computing is a sum of a very large number of random variables. So what is the variance of this return that I compute from my simulations going to be, from my episodes going to be? The variance is going to be the sum of the variances of each of the rewards. It's going to be very large, right? So which means this Monte Carlo method, if I want to employ the Monte Carlo method, I have to run through a large number of episodes before I actually begin to come up with reliable estimates for these values that I was trying to compute, which goes back to your point. Even in a small state space, it's not really going to work very well, right? Although it's mathematically very nice. But then it sets the basis for our surprising results, okay? And here's how our first surprises comes in. What we want to do is to learn online. As I'm playing the game, right? I'm the fly, I'm trying to catch the spider, and I move to this, I say, I have this policy, I fix my policy, I'm still trying to find the value for the policy, right? And then I'm at some state and say, okay, my policy says go there, so I go there, and the fly goes away, right? Then I can say, under my current policy, the value of being distance 3 maybe is not so great because this fly just moved away, right? So as you're going through the game, or as you're going through the process, you would like to be able to continue to update the values for your states without actually waiting for things to turn. You want to learn from what is happening. The environment is not behaving in a friendly manner. I should decrease the value. The environment is behaving in a nice manner in response to my policy. I should increase the value for the state. This is the kind of behavior you'd like to see. And the Monte Carlo method doesn't actually allow you to do that. But then, here is our surprise number 1, right? And surprise number 1 is a very simple, trivial little formula, which is this. This is the beginning of surprise number 1. There's an end to it as well. Now consider first, what am I really doing when I'm computing my values under the Monte Carlo method? So when I'm computing the values under the Monte Carlo method, I have SAR, dot, 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 right? And so let's assume that these guys are, all the state A. And let me assume that this one, the return over here is G1, G2, 3, G4, G5, right? So you're saying value of A equals, summation I such that state equals A, Gi, right? Or however many times you actually visited the state. This is what you're trying to do, correct? So this is the equivalent of this guy here. You have a large number of variables, observations of a variable I, and you're trying to estimate the mean of the observations of that random variable. So you're summing and then dividing by the number of observations. So focus on this formula over here, mu k. I can write this as mu k equals, or I can rewrite this as k times mu k equals summation I equals 1 to k xi. So I have k observations, correct? So k times mu k, I'd have a 1 over k over here. I just moved the k to the left. So k times mu k is some summation over all k observations of xi. But then one step earlier, my estimate would have been k minus 1 times mu k minus 1 equals summation I equals 1 to k minus 1. Why do I keep writing x? Mu has to be x. Xi. Correct? So nothing really surprising. So this is simply going to be k minus 1 times mu k minus 1 plus xk. This guy. Correct? Because I can just pull out the last element from here, and that's the same as the lower sum. And the lower sum is simply, the scaled version of the estimate of mean after k after k minus 1 observations. So I can just write it out like so. Which leads me to the second formula. Mu k equals k minus 1 times mu k minus 1 plus the kth observation divided by k. So let's take that for granted. Now I can go back and I can reorganize my terms. Which is like so. I know that mu k equals k minus 1 mu k minus 1 over k plus xk over k. Correct? Which is going to be simply mu k minus 1 plus mu k minus 1 minus mu k minus 1 over k plus xk over k. I just pull this out, which leads me to this amazing little result, right? This amazing little result, which is so trivial to derive, is that when I get a new observation, in order to update my estimate for the mean, all I have to do is to add the difference between the observation, some scaled version of the difference between the observation and the current estimate of the mean, a little correction factor to the current estimate of the mean. And these correction factors are guaranteed to shrink as you get more and more observations. Right? Very nice. So this is whoever observed it was a pretty smart person. Now you can generalize this, and I can just replace this 1 over k things falling off, and write this as some alpha, which is to say that every time I see a new observation, I'm going to look at the difference between that observation and the current estimate and add a little small fraction of it back as a correction to my current estimate of the mean, right? And this is guaranteed to be, optimal if that alpha is 1 over k, but other values of alpha where alpha is less than 1 would work just fine. Alpha equals 1 will not work, because if alpha is 1, you're just going to say mu k equals the latest k, xk, right? And which is not really going to converge. So here's a little simulation of how this little simulation, this little iteration behaves. As I keep adding more and more observations, if I use the original formula, which is the guy to the top left, my estimate for the mean converges according to this blue curve. And you can see that after just a few observations, it swings around a bit and then quickly converges. But then observe that it swings around, right? Because in the beginning, k is very close to 1. You're literally just following the latest observation. It's only towards the end that k becomes k is large, and the correction terms keep getting smaller and smaller. And so initially the variance is quite high, then the variance becomes very low. I can choose other values of alpha. If I choose other values of alpha, as alpha gets smaller, the variance of the estimate is going to decrease, but it's going to converge to the true value slower and slower and slower. It's a trade-off, right? So, but most values of small, any small value of alpha would also just work just fine. Now, the correct equation, the blue curve, is unbiased and converges to the true value. The equation with alpha not equal to 1 over k is biased, in the sense that in the beginning you're guaranteed pretty much that you won't be getting the correct answer, right? But as the number of observations increase, both of them will converge to the same value. And the nice thing is that if you're using alpha as opposed to 1 over k, things don't swing around wildly in the beginning, making things a little more amenable to prediction and control, algorithmic control. Anyway, so now let me go back to my value function. This was the value function that I had for any given state, correct? And this, I can rewrite it using just the same, as I'm going through my episode, at each time, I would like to, so this is the first one says I have to go through all of my episodes, and then I have to add up the returns over all of my episodes, and then divide by the number of times a particular state was visited. I'm going to modify this and say that every time I visit a state, I'm going to make a little adjustment, right? Or instead of dividing 1 over ns, I can just use an alpha. Does this solve our problem? Is this online? I need GT, right? So this guy is a problem. Remember, GT was the return, meaning you were summing the discounted returns, rewards, all the way to the end. So just to compute GT, at any point you stood, the reason we were doing this whole, when we were doing this Monte Carlo business, you ran through the episode, then you went back to the beginning and you walked through it and said, what was the return from here? And you looked all the way to the end to compute the return. What was the return from here? And then you looked all the way to the end to compute the return. So this guy hasn't solved the problem at all. He just stated it slightly differently. But then I'm going to make a little trick, use a little trick. Surprise number 1. Actually, surprise number 0.5 was the little recursion I just showed you. Let's round it up to surprise number 1. We know that GT equals a rewarded time at that time plus the discounted return at the next time. Correct? Very simple, because this is how it was defined. So I had the return over here is going to be this reward plus the discounted sum of the rest of these guys, which is the discounted return at the next time. Right? This is just easy. So why do I need to use this return itself? I can use an estimate for the return at the next time. Right? And what is the best estimate for the return at the next time? There are different ways of estimating this guy. But no, I was just showing you the derivation. But you know what? my best estimate for the return at the next time is the expected value of that return, which is going to be the value of the state that I ended up at under my current policy. My current estimate of the value that the state I ended up at the current policy. So observe over here that I actually have, it's not as if it's completely online anymore, right? It's still slightly less than online. But what happens is that anytime I visit a state, right, the moment I visit a state, so here's what I'm doing. So let me just say I have these guys, right? The amount of time I spend opening pens, I could cover a lot more of the class. We've seen that 2 times. Yeah. So let's say this was A, B, like this is C, and maybe this is B again. And you know, in my little world, there are only 3 states. So what happens over here? I'm going to start off by saying V pi of S is whatever, some initial value. Okay? Then I begin walking. I arrive here. I note that this is state A, but nothing has changed. I take my action and I end up over here. Now I know what the successor of this guy was, right? So now I can go back and say V pi of A is going to be V pi of A plus gamma times, and what would this be? Not, this is going to be, this is plus R, because this was, what have I got, right? Plus gamma times, wait. Let me correct myself. Here is my estimate. I'm going to say G of A equals R plus gamma times V pi of B, because this is where I ended up after I go back. And I can plug this guy in to my formula, which says that V pi of A is, I shouldn't be writing in red. I don't think anybody's actually watching the streaming. If they did, they'd complain. So I can write V pi of A is going to be V pi of A plus alpha times this term, correct? Which was, what happened? Are we still on? Okay. V pi of A, right? So this was the little recursion that we saw. This is the current estimate of the value for the state. This is my estimate for the return at A. I plugged it in to this incremental formula. And now I have an update for my V pi of A. So observe what happened. I didn't actually go through the whole process. So I only went through till here. I started through the process. I initially visited A, took my action, ended up at B, and then I successor of A, right? So then from that I can come up with my estimate for the return at A. I can plug it into my incremental formula over here. And I update my value for A. Okay? I continue now. So I've come to B. I take some other action. I get some reward, right? So, and then I ended up again at A in this case. Now what am I going to observe? At this point, I know that I can actually compute an estimate for the return at this point, at this guy. That is going to be G, I'll call this G2 equals, I should have really put times over here, so let me call this R2, E2, right? R3. It's going to be R3 plus gamma times, I ended up at A, correct? This is going to be V pi of A. And what is the correction? What is the state value that I'd actually be updating now? I'd be updating the state value for this state. That's going to be V pi of B. It's simply V pi of B plus alpha times, this would be R3 plus gamma times did you see exactly how the whole thing happened? Right? I took one step forward, and now you could use I know which state I'm in, and use the estimated return or the expected return for that state within my formula, and therefore now I get an estimate for the return at the previous time, right? And I can use that to go back and correct or update my value for the state at the previous time, right? So we're going to call this, now here's the beautiful thing. This is just like what we wanted, right? I move towards the fly, I go to the corner, I say, oops, there's no fly. Let me go back and correct my value for the state of the previous instant, right? Okay, now I'm going to move towards the fly. You go there, oops, there's still no fly. Let me go back and say the value was worse than I thought it was, right? And this is the process you're actually doing till you actually catch the fly. So you're incrementing your beliefs, you're updating your beliefs as you go through the system without waiting all the way to the end. So I can sort of write this whole thing down as this is called temporal difference learning, in the sense that you're looking at the difference between what you observe now and what you thought one instant ago or some n instance ago. And this temporal difference is being used to update your beliefs in the values of the states, right? So what we had over here was a one-step look ahead. So you went up one step and then you corrected the value for this guy. So I'm going to call that TD1. Well, not me, but whoever initially came up with this terminology called it TD1, right? So here's how TD1 works. I have a current value for the state at time t, and then I take whatever action and I end up at the state at time t plus 1. And so now I can compute a correction term, what we'll call the TD error, which is this guy here, right? How much you're going to have to correct the value term by, which is the estimated return at t minus the current value of the state at t, right? Current estimate for the value of the state at t. That term you're going to multiply by some alpha, which is the scaling factor, and then you add it back to the current estimate for the value. And this is TD1, right? Very easy. So just the whole thing written in a little algorithmic form. Any confusion so far? Very straightforward, nothing really complicated. I said it was a surprise. I'm pretty sure that, if left to your own devices, you would not be very likely to have come up with this solution very quickly, which is why it's a surprise, but eventually you might have. It's not that non-obvious. What is non-obvious is going to be surprise number 2. Okay. Now given this, what is your next best guess? So if I wanted to improve this, what would your obvious choice? So let me actually begin introducing timestamps over here, just so that you can sort of visualize what you really got, right? So here is what happens. Let me call this as 0, S1, A1, R2, S2, A2, R3, S3, A3, R4, S4, A4, R5, S5, A5, R6, okay? So what we did over here is that when we began the process, we initially said V pi of state equals 0 for all states. We began walking down. We first hit A, then we continued walking, hit B, and then went and updated the value for the state A, right? If you wanted to improve on this process, what would the most obvious thing for you to do? Obvious thing be? You would increase the amount of evidence that you actually used, right? Instead, you would say, I'm going to go here, I'm going to walk here, and then correct this one, right? So in this case, your G1, the estimate for the return at time 1 is going to be R2, right, plus gamma times R3, which is going to be here, and then plus gamma squared times V pi of A, because this was A again, right? So once you walked here, then you'd go back and correct the first guy. And then you just use V pi of A is whatever, V pi of A plus alpha times G1 hat minus V pi of A. Right? Yes?
So when K equals the number of steps, the number of states in total, is it kind of just like the Monte Carlo?
Yeah. Right? So now this is a two-step look ahead. And this two-step look ahead, I'm going to call it, TD2. I can have an n-step look ahead. I'll call that TDN. You know, the whole process is obvious. I don't even have to work through the math. Now here's the really cool thing. This little example, we have, it's 9:56. So I'm not going to go through this example, but it's easy to show that this temporal difference learning actually does better and give you what seem to be correct answers when Monte Carlo doesn't. So here are a bunch of episodes that we got from this little process, where when you're in state A, you go to state B with a probability of 1. When you're in state B, you can go to one of those two situations with different rewards with different probabilities, right? And if you simply compute all of the terms, the value terms over here using simple Monte Carlo, you're going to find the number of times you visited A was 0, was 1. I won't work through this. But what you're really going to end up is you're going to get the wrong value. You're not going to recover this actual model using Monte Carlo. But then if you iterate through the process using temporal difference in just 2 rounds through all of the data, you're going to get you're going to actually recover this model, right? And I would have worked through it. But what I want is move ahead, right? The further you look ahead, the better your estimates get, because you see you're gathering more and more evidence. You also get more variance, right? Because each instance of evidence is actually giving you an additional random variable that you're adding. But then here is what Vital was pointing out. If you are at infinite look ahead, you're back at Monte Carlo, right? So what have you gained, right? You're not really very much. So I'd like to have as much evidence as possible, but what is the best kind of evidence? So answer is, so here's what it is. This is what TD1 does. It's a one-step look ahead, right? Or rather a one-step look behind. Better way to look at it. But think of it as, you go back and look, right? This is a 2-step look ahead. This is a 3-step look ahead. This is in Monte Carlo. It goes all the way to the end. Now, all of these, as you keep increasing the amount of look ahead, you're including more and more evidence into your estimate. But then you're gathering more and more of a lag. You're potentially trading off seeing more evidence with having more variance, right? And in the limit, you're back to where you're really not doing anything online at all, right? So which of these is the optimal best one to do? Which one do you choose? And the answer is, let's not choose any of them. Okay, I'm going to use all of them. So what I'm going to say, I want to have more evidence, but then because it has more variance, I want to decrease its contribution, scale its contribution. So I will say that I'm going to use the TD1 estimate for G with weight 1 over 1 minus lambda. I'm going to say use the TD2 estimate with weight lambda times 1 minus lambda. I'm going to use the TD3 estimate with lambda squared times 1 minus lambda. Why this particular choice? Because when you add all of these weights, they sum to 1. So eventually you're going to get one fixed estimate, right? And so this is what we will call TD lambda, okay? Here, I'm actually going to be adding, I'm taking the estimated return. So GT parenthesis n is your estimated return with an n step look ahead, okay? And I'm taking a weighted sum of all of these look aheads from 1 through infinity, and then plugging them into my update formula in order to get in order to update my value estimate. But here's the nice thing, because this guy actually combines a whole bunch of estimates for G. I expect to get some kind of a golden mean between using more evidence and having lower variance, right? What is the problem here? The problem is I haven't solved anything. This term also includes GT infinity. So I started off with saying I don't like Monte Carlo. Then I made the problem worse by saying not only am I going to use Monte Carlo, I'm going to use everything in between, right? So it looks like I just went a big circle and slapped myself on the face. Not a very good idea, but it turns out something magic happened. Infinity is a beautiful thing, and although many mathematicians despise the concept, it actually works out very nicely in our favor here. So TD lambda looks into the infinite future. So we must have the rewards of all the rewards of the future to compute our updates, and it would seem it doesn't help. But then here is what it looks. Here's what you can think of. Here's a different view to the model problem. What you did was you walked the entire path through an episode, right? Went to the end, then you went back to the beginning and said, what would my estimated return be if I only looked one step ahead? What would my estimated return be 2 steps ahead? And you did this for every one of these guys, right? And then you added the entire lot with weights, 1 minus lambda, lambda times 1 minus lambda, lambda squared times 1 minus lambda, and so on, okay? But then you are thinking of this selfish perspective, right? How much do I get to update my own value, right? Then let's go back and let's make a philanthropic perspective. How much do I help others? So if I think of it from a philanthropic, for every selfish guy, for every receiver, you need a giver, and vice versa. Things balance out. So if you look at it from the giver's perspective, who is this? Who are all the people? I can just mirror the entire picture, right? I can take these dots and push them out into a line. So let me look at what my current guy is contributing to the past. It's a mirror of exactly what we have over here, right? This guy is contributing 1 minus lambda of his value to the value for the state 1 time instant ago. He's contributing lambda times 1 minus lambda of his own value to the state 2 time instance ago. Lambda squared times 1 minus lambda of his value to the state 3 time instance ago, and so on, right? So all current rewards, I don't know what this text means. The current reward contributes to the updates of all the states that have been visited until now from the beginning. I can mirror this whole image because I'm looking all the way to infinity, so I can look out all the way to the beginning, right? And so here's what it gets, right? So if I were walking through all of these guys, right? So let's say the states were red, black, red, yellow, yellow, red, black, and here, right? So this reward over here is contributing 1 minus lambda to the black state, then the lambda raised to 5 times 1 minus lambda to the black state over here. It's contributing lambda times 1 minus lambda to this red state here, and lambda raised to 6 times 1 minus lambda to the red state over here. So now I can define something called an eligibility trace, right? An eligibility trace is how much is this guy contributing to each of the states. Observe that he's contributing to all of the states. He's contributing to the black state. He's contributing to the red state. He's contributing to the yellow state. How much is he contributing to the red state? He's contributing lambda raised to 6 times 1 minus lambda plus lambda raised to 3 times 1 minus lambda plus lambda times 1 minus lambda, right? These were the three instances in the instances in the current episode that the red state was visited. And so it's contributing the sum of these three guys to the red state. In the current episode, the black state was visited here and here. So this fellow is visiting so far. So he's contributing 1 minus lambda to this one, lambda raised to 5 times 1 minus lambda to this guy, right? I have to add these two contributions. I can just add these things up. And if I add all of the contributions up, they must sum to 1. All of the contributions to all the states, right? And so now I can define something called an eligibility trace, which says that the eligibility trace for any state, which is basically saying how much am I contributing to any state S in the past, is going to be whatever contribution I've already had plus, you know, discounted by gamma plus 1. So I can go back and say time instant. So I have basically every time I move up one step, right, I am discounting everything down by gamma. So this is gamma term, the gamma that's actually being discounted. And then I can say what is my once I come here, what is the contribution of this guy to the red state, right? I can say, was this red? No, I'm not contributing anything over here, right? Was this red? Yes, I'm contributing something over here. So I actually have a check as to whether I've actually visited the state at time t or not. And so the eligibility trace is simply gamma times the eligibility trace at time t minus 1 plus a check on whether the state was visited or not. Basically, if you work this arithmetic out, you're going to end up with this formula. So here's what we can actually do, right? I can now go back and update my formula and say that the TD correction factor, which is exactly what we had earlier, is going to be multiplied by this eligibility trace. In other words, what happens is once I come here, I'm going to go back and update every one of the states that I've visited so far with my own contribution, right? So instead of looking forward and getting everybody's contributions towards me, I can turn back and include my contribution to every one that has occurred so far. Now I won't go through the arithmetic because you will forget it before you leave the class. This is going to be on the slides, but it's the concept that's clear, that's important, right? And so this business about how much I'm going to contribute to each state is composed into this eligibility trace, which is basically, as we saw, the sum of these guys. Lambda 6 raised to lambda raised to 6 times lambda minus 1 plus lambda raised to 4 times lambda minus 1 plus lambda times lambda minus 1, right? I keep going back, and if that state was red, I add a new term, right? So this is TD lambda. We managed to get the effect of infinite look ahead by turning around and getting an infinite look behind. Looking behind to the end of time turns out is exactly the same as looking backwards to the beginning of time, right? So every reward updates the value of all the states leading to the current reward. I got a current time. Instead of just, adding to whatever happened in the future, I'm going to go back and add to whatever happened in the past. When lambda is equals 1, this is exactly the same as Monte Carlo, right? And when lambda equals 0, what is this? just TD1, right? You're looking at a one-step look ahead. So what we've seen is this is TD lambda, very nice, very easy. This was surprise number 2, right? This business of TD lambda, in the sense that I can get the effect of infinite look ahead by turning around and doing an infinite look behind. So I'm still left with an online update rule, which keeps learning as I walk through my experience. But what happens now is that if I'm the spider and come to a current state, and I say, damn, there's no fly, right? I'm not merely going to go back and correct the value of the state that I just visited. I'm going to go back and correct the values of all the states that led me to this current point. So if you go back to our very first example of chess, when you won the game, you didn't want to just increment what happened just before you won the game. You wanted to increment everything that happened all the way to the beginning of time, right? So this is basically what you're doing, except it's even more subtle. You can, even before the game ends, you can begin assigning values to states. So what we've done so far is to see how, given a policy that you follow, you can actually learn values for all of the states using that policy, right? But what did we really, so this was planning, I mean this was prediction, right? What did we really want to do? We wanted control. We wanted to know how to choose a policy. What is the best action to take at any particular state? And so now we want to update this guy. Now remember what we were doing earlier, that when you're doing the policy iterations, you chose a policy, you found the values throughout this complicated iteration, then you updated your policy and repeated the process. Not a good idea. That means you're going to have to do this many, many times. But then if you remember the value iteration, what we did was that at each time, in each iteration, you just kept updating your values, the optimal value for each of the states. If you wanted to compute policies, you could update your optimal action value functions and then learn your policies, right? If you're going to have to do something very similar now, I'm going to stop pretty early, which means I may actually continue for 20 minutes on Wednesday, but not much more. This is the solution we saw so far only computes the value functions of states, which is not sufficient. What we really want to compute is the optimal policy from the value functions alone. And for this, we'll need extra information, namely transition probabilities, which we don't have. So instead, we can use the same method to compute action value functions. For the basically, for the optimal policy in any state, you choose the action that has the largest action value for that state. So value versus action value. Remember that the greedily optimal policy at any state chose the specific action that had the largest action value for that state, right? So basically, these two formulae are saying the same thing. The term above is the current reward plus the action value for the next state. Now, so choosing the optimal value by itself was quite useless, right? In the Markov decision process, where I actually gave you the transition probabilities and everything else, if I gave you the values for any policy, you could compute the action value functions. But in the reinforcement learning setting, where I don't give you the transition matrix, if I simply give you the optimal values if I give you the values for all the states under any policy, it still does not help you learn the action value functions. Because in order to go from the value to the action value function, you needed the transition matrix. And we do not have the transition matrix, right? So what this means is that now we are going to have to use exactly the same process that we just saw for learning value functions of states under a policy, except now we are going to be learning action value functions, right? And for that, I'll actually skip the slides. What's it we are going to have to do? When we were actually performing the value iterations, what we did was we started at any state, took an action, got a reward, ended up at a state. And all you needed to know was what is the next state going to be in order to update the value for my current state, right? If instead I'm using action value pairs, state action pairs as my basis, what do I need to know? I need to know, in addition to the state, what is the action I'm going to perform in the next instant, right? So I would be at any state, I perform some action, got a reward, ended up at some state, and then I chose an action. And I can use this guy to update the action value function for this pair, right? So I need to take an S, I need to be at an S, I need to perform an A, I get a reward R, I end up at some other state S, and then I perform another action A. And that is the entire sequence I need to perform before I can actually go back and update my state, the value associated with my state action pair, right? So it's SARSA, they call the algorithm SARSA. But this is exactly what we just saw, the TD update, except TD updates applied to action value functions, right? So this is called SARSA, and this I'll actually stop here because it's 10:16, right? But this is the basis for Q learning. You're learning cues. And because you learned cues, now from the cues you can choose the optimal action or optimal policy for any state, right? In fact, the rest of it is fairly obvious. Something interesting happens over here. If I'm actually going to be performing an action out here, in order to obtain this action out here, compute the value of this state action pair out here, I don't really need to perform the action, right? Because you're not looking at the outcome of the action, you're not looking at this reward. The action can be completely hypothetical. And that leads to off-policy learning, right? If the action that I predict in order to update this action value for the state that I was in previously is actually the action that I will take, it's called on-policy learning. If the action that I predict is different from the action that I actually take, it's called off-policy learning. So we'll just go through it quickly. Would you mind if I didn't do the class? It's fun stuff, right? The slides are up there, so I'll actually poll on. Jerry can do it. Okay, so Jerry's going to complete the rest of this lecture, and then he's going to begin talking about, yes, first off-policy learning, deep Q networks, and action replay. Perfect, thank you. So lovely. Yes. Thanks, folks.